summary of everything that we have done so far relating to linear regression. Okay. The story starts with data. So this is your raw data, which is usually in the form of pairs of X and Y values. You want to summarize this raw data as a linear fit. So let's say you have some data that looks like this. You would like to draw a line which represents the data equivalently. So we have a straight line, y equal to mx plus b, and the whole process of fitting is to evaluate m and b. So I'll write here. Fitting or regression entails evaluating fit constants that minimize SI. I'll just say yes. So I'll wait for people are intently writing, so I'll wait for one more. Yeah.
For the V with the
mu. Greek letter mu.
Are they the same mu, or is whenever it's the for the three, the quadratic?
Yeah.
Is that stating that it's for quadratic? So like up there, that's for quadratic, or is that for any mu?
This is for any mu. This is actually a very good question. All this is true for any regression, not even linear regression. It could be quadratic, polynomial, whatever nonlinear regression you might do. This is a general principle.
Okay, so those two for the quadratic and the two parameter, those are the same mu. Although that.
See, for linear fitting, it will be n minus 2. For quadratic, it will be n minus 3. For any polynomial, it will be n minus m plus 1, where m is the order of the polynomial. Okay, so it doesn't have to be always a polynomial regression. If it can be any regression, it is just the number of fit constants. So what is your question?
Just the way you wrote the mu. Like how that one doesn't have the loop at the top. Like like velocity versus like it.
I don't know if I thought they both are the same. You want I'll write both of them without the loop.
Okay, just making sure.
Okay. So if you are all done writing, I would really like you to listen. Okay. So the process of fitting is to evaluate the fit constants that quantitatively represent the data. And for linear fitting, it's only two parameters, m and b. So you can set up two equations in two unknowns, and you can actually directly have this formula ready if you want to calculate the slope and intercept. Okay, I'm just if I rearrange this and solve the two equations, I'll get m and b. We did examples on these. Now, once the m and b values are calculated, now we have to evaluate the quality of the fit and the confidence on the fit. We start by defining an error, which is the prediction of the fit at a given x value, let's say x1 or x2 or whatever, minus the corresponding y value. This is the deviation at a given value of xi. Okay, so like if it's like asking, if I have a data point here, okay, and I have my fit line, this is y at xi of the fit, and this is yi. So it's the difference between the two, which will be ei. Okay, so we take the square of ei so that we get rid of the sign, and we sum it up to get what is called as the standard error of the fit. It's the total deviation squared, or the total of deviation squared. And then we get or define degrees of freedom, which is number of observations or data points. So 1, 2, 3 up to n, minus the number of fit constants. And for linear regression, that will be n minus 2. Okay. Once you have the standard error divided by the degrees of freedom gets you what is called as the standard deviation. And then we get the corresponding t statistic value. The t statistic multiplied by the standard deviation is the confidence interval. So if you have a fit, you can get a band around which the true value is likely to lie, and this band is the confidence interval. The mistake I did last lecture is that I forgot the square root of n factor. So now I want to fix that. So confidence interval formula includes the t statistic multiplied by the standard deviation divided by the square root of number of observations. What is the implication of the square root of n? What happens to the width of the confidence interval as you make more observations? 74, my God. What happens to the width of this interval Ci as you make more observations or as you have more data? It reduces, or in other words, to put it, the confidence interval reduces, or the confidence of your fit or reliability of your fit increases. So again, good practice to include more data points to get a better fit. Okay. So this we did couple of examples. Are we good up to here? Any questions? Shall we just look at the examples we did? You have a question? All right, you already did this. This is also on the Canvas page, so no need to write or do anything. Just listen, please. So here is the data, X and Y values. Okay. So this is given to us, and we are asked to fit a linear regression to this. And we start with the formulas for M and B. Now, in your exam, I'll provide you these X and Y values, step 1. I'll provide you the sums of X squared, XY, X cube, everything. All the sums that you need that appear in your formula for B and B, they'll be provided to you. You don't have to do this calculation. Okay. So let's say you know the formula, you plug it in, the values for the summations, and you can get B and M. Is everybody okay up to this point? If I give you a column of data, 2 columns of data, you can get M and B. We are all good? Good? Yeah. All right. So now we want to calculate the confidence interval of this fit, which we do by first computing what is the Y fit value. How do you compute Y fit? You take the X value and feed it to mx plus b and compute this number. This Y fit minus Y is the error, EI. Okay, and then we do EI squared, and then sum of EI squared. This is what I call the standard error of the fit. Standard error of the fit. Okay. Standard error of the fit is sigma EI squared. Then we have number of observations to be how many? 10. Some not clear? It is either way is okay because the error is squared, so that will remove the sign. You may see it as y minus y fit. I can see it the other way, but we are both right. Okay, so you have standard error of the fit. Are we together up to here? Standard error of the fit. Yes. So then you need to look at the number of observations, which is 10, and degrees of freedom, which is 10 minus 2, 8. Okay. So I take the degrees of freedom, I take the standard error, divide them to get the standard deviation. So standard deviation is square root of S divided by nu. So this is an important step. Once you have the standard deviation, then you multiply that with the t statistic, which you will be given a lookup table. Remember the table we saw in chapter 3? You'll be given the same table which you need to look up and write down this value in your quiz or exam. Okay? And then the confidence interval of the fit is t statistic multiplied by the standard deviation divided by square root of number of observations. So it is this value t statistic multiplied by standard deviation divided by square root of 10. Okay, and that value comes out to be 0.7766 in this example. In your quiz, you will be given a table of data, asked to evaluate the regression parameters M and B, and asked to compute the confidence interval. So it is basically a 4-step process. You have to get the standard error, standard deviation, t statistic, and then the confidence interval. None of the intermediate steps is like going to be explicitly asked, but you have to go through the steps. Okay. All right. So if you have the confidence interval, how do you actually draw this band or the confidence interval around your fit? What is this dashed line and what is the lower dashed line? What is, or in other words, what is the meaning or implication of this confidence interval? What did we learn in chapter 3 about the confidence interval of a mean? It is the range in which true value could lie with a certain probability. That last few words are also important. How much, what probability or what odds are you giving it? In this case, 95%. So when I take any value, let's say for example, I choose a x value of 5. At that x value, there wasn't any original data, but my fit will predict something. Let's say it predicts something like 6.5. It's like saying 6.5 plus CI and 6.5 minus CI is likely to contain the true value of y with 95% chance or probability. That is why you want to, whenever you replace a bunch of data with a fit, you also should calculate this confidence interval so that you can tell whoever is using your fit how much confidence to place on your regression. And when will this happen? Suppose you are the engineer responsible for collecting data from an experiment and you are the only person handling the raw data. You perform a regression, you summarize that into a nice, neat equation, and you send it to the next engineer in your team who will not see your original data. That next person is just going to see your fit, and he or she has to know how much confidence to use on your fit. You could have gotten your fit from a really terrible data or from really extremely good data. All that will reflect in which quantity. If you got excellent data which have very less noise, where will that show up? The standard deviation. If you, that's a very nice answer. That is, if you had excellent data, it will show up as a low standard deviation. Suppose you have excellent data, but you made very few observations. Let's say you did only 4 observations and you are fitting a straight line to that trend. It can still be sketchy, and where will that information show up? How will the next guy know or next woman know that your confidence interval or your regression is not trustworthy? If you had only 4 observations, even if you had excellent data, the confidence interval will be wider. So the width of the confidence interval can be interpreted by the next person in your team, either as you did a lot of observations to make it small, or you had terrible data, or you had good data. Everything can be decoded from the width of the confidence interval. Okay, so this is how we would get this. So how do I generate that data? I go back here and I do yfit plus CI and yfit minus CI. So I get two more columns. I plot them against X, and that's why I get three curves here. The top curve is yfit plus CI, the middle curve is yfit, and the third is yfit minus CI. Okay, but at least for your exam, you should be knowing how to calculate the CI. Plotting it comes later, maybe in your homework or something. Question.
Um, so is there any way you could go over TP submu? Like, I guess.
How to look up the.
Yeah, with a given mu value. Like,
So I did that here using uh, using Excel's built-in software to get me TP value. But simply put it, you remember that table I gave you, it had three columns for different values of confidence and then rows which denote values of mu. In our case, mu is 8 and our confidence is 95%. So you would look up for this 95% column, mu equal to 8, and you would get this value of 2.3 something. So you should, I mean, I don't have, do you have the copy with you? Because if I open my, wait, maybe. I can, don't worry about it. I got it. All right. Yes. Yes, that Excel has the revised Excel with my mistake fixed, everything has been posted. All right. So here is our all right, here is your T statistic table. Our degrees of freedom is 8, and I think the third column is 95%. So 8 degrees of freedom, 95% gets you 2.306. Same value that Excel spits out. Yes, in the exam you have to do it manually. So you get the confidence intervals, and that essentially closes out the analysis where you went from raw data to a fit. Okay. Now let's briefly talk about quadratic regression. Okay, that is instead of fitting a linear curve, suppose we are interested in fitting to our data y equal to ax squared plus bx plus c. Suppose we are interested in that, we would still need to solve for we would need to solve for a, b, and c, and you would do that by setting up three equations in three unknowns: sigma y equal to a sigma x squared plus b sigma x plus cn, and then sigma xy equal to a sigma x cubed plus b sigma x squared plus c sigma x, and then sigma x squared y equal to a sigma x to the fourth plus bx cubed plus c x squared. All these sums will be given to you. Don't have to be scared about evaluating these during the exam. And then you use your method of choice to get A, B, and C. And then the rest of the analysis actually weirdly proceeds exactly same. Get the standard error, which now will be defined as y fit equal of x is ax squared or xi plus bxi squared or bxi plus c. EI is still the same, y fit of xi minus yi, and rest of it doesn't change one iota, except the degrees of freedom has to be calculated as n minus 3. Yeah.
Does the N carry to both of the, put the C down there too, or is it only within the first one?
This one?
Yeah, that's the N.
Yeah, and number of entries.
Does it go for the other ones too, or just that first?
So C times sigma x, C times sigma x squared. First row is C times n.
Okay.
Yeah. So you would get the standard error of the fit, get the degrees of freedom, get the standard deviation, read up the t statistic, and get the confidence interval. Same sequence. Okay. See, some of this I say, like maybe I can ask you a few things in the exam, but there are things that I won't be able to ask in the exam, like making you plot it, get the confidence interval. This is where the real learning is. It's not, you shouldn't be studying only for the quiz, because what I'm teaching you could be later useful as well. So try to absorb it, okay? All right. So now let's look at an example of quadratic regression, which we did last time. Now I just want to go over it and also show you the confidence intervals. So this is problem 20, okay, problem 17.20. It's all in the Excel sheet. You don't have to write this, so look up and listen. The data is given to you as X and Y. Usually, in real life, nobody is going to sit behind you and say use quadratic regression or use polynomial regression. Nobody is going to tell you that. You have to develop the intuition of plotting the data and then thinking about what function would reasonably describe this. So let's say we start with quadratic. You get your x squared, x cubed, x to the fourth, etc. All this will be given to you in the exam. You can solve for A, B, and C. Yes or no? Do you see how to do that? Yes. So you can get A, B, and C, and using A, B, and C. So I did that by just using Excel itself, but you would actually do that. And using A, B, and C, you would compute Y fit. Okay, Y fit is ax squared plus bx plus c. Okay, and then error is Y fit minus y, and then I have error squared. Now, see, this is the money shot. This is the 4 numbers that I will make you calculate in the exam. Standard error of the fit, standard deviation, which is error divided by degrees of freedom. How many is the degrees of freedom here for this example? We have 7 observations. 7 observations for quadratic regression. What is the degrees of freedom? N minus 3 or 4, right? Right here I have made a mistake. This minus 3. Okay, so then I have my standard deviation, which is standard error divided by degrees of freedom, square root, t statistic, and then confidence interval. So I have these 4 numbers computed, and then I computed y fit plus ci and y fit minus ci, and here is the graph. If I take any particular value, let's say x equal to 1, and I make a prediction that is something like 800, once again, what does the width of the confidence interval signify? In words. You might be asked to write this down, like interpret the confidence interval. This could be a real question. Yeah.
It determines on how big your data is.
That is very broad and qualitative. You have to precisely say
the probability of the amount, like the percentage of the data points contained. Like if this is 95% of the data points.
Okay, the way it is usually stated is it's the range within which 95% of likely values lie, or it is the range in which the true value can be found with 95% probability. Yeah. That's how you state it in words. Okay. So this is quadratic regression. Suppose if not that I'm going to ask you a 4th order or a 5th order regression, but if comes up in your work or research, how would you do that? You have your data. Instead of saying I want y equal to ax squared plus bx plus c, let's say I'm telling you y equal to a1 x to the 4 plus a2 x cube plus and so on up to a naught. So this has 5 parameters. So you need to set up 5 such equations and get them, but the procedure is more or less the same. For the first, I mean, you would basically write the first equation is sigma y equal to a1 x to the 4 plus a2 sigma x cube plus a3 sigma x squared plus and so on a naught n. It's like literally multiplying one more x to generate more equations. Okay. This can keep working for any polynomial or any order. Okay. All right. So this was about, at least in our course, we will stick to quadratic, not to Euclids. Okay. We'll stick to quadratic. All right. The other concept we saw is about linear transformations. If you're done writing this, I can wait a minute and then start. So for the exam, the quiz, you can definitely expect one question in which you are given to do a linear fit and compute the confidence interval. This is coming. You can take my word. Okay. Okay, actually, there's one more concept I wanted to mention today. How many of you have done fluids lab already? Fluids lab course you've done? You're in it right now. Is there any experiment to measure the viscosity of a fluid? How can you describe the experiment?
Well, there's many experiments that we do, but
So the typical experiment to measure viscosity of fluids is if you have a tube and let's say your fluid is water or air, you would send it through and you would have a pressure tap here and a pressure tap here so that you can get the pressure drop across a section of known length. Okay. And a flow meter is also added in series so that you can get the flow rate going through. So if you plot the flow rate versus the pressure drop per length, theory says Q is equal to pi by 128 mu multiplied by delta P to the L times 10 power D power 4. D is diameter of the tube. Okay, this is fluid mechanics theory that you can derive this equation. In an experiment, you wouldn't actually measure the length or the diameter, but you do know that in a given experiment, diameter and length are fixed, whatever they are. So you would try to vary the pressure with which the fluid comes in and measure the flow rate at different values of delta P. So let's say you would do something like this. Like this. You can fit a straight line, okay, and the straight line would have a slope. Now, according to theory, the slope should be inverse of the viscosity or should be related to the viscosity inverse. So using the slope, you can get the viscosity. Okay, that is if you take a plot of Q versus delta P, you can use that to get the viscosity. So one application of this linear regression is to take experimental data, have a template equation, and then use the template equation to recover something that is physical. something that is important for you as a measurement. Okay. All right. So you recover this slope. If you look up property data like viscosity, they not only tell you the value of the viscosity, but they also tell you something else. What do they tell you? Like they say viscosity of air is 1.8 times 10 power minus 5 Pascal second plus minus 2%. What is that plus minus 2%? It is the confidence interval on that slope. So if you are computing slope, you should also be able to compute the confidence interval of the slope and the intercept. Okay, this definitely is not coming on the exam, but I just wanted to make that mention that your slope and intercept also have uncertainties, which you can calculate if you care to, and it can easily be looked at. Okay, but the uncertainty on the slope, the confidence interval on the slope, and the confidence interval on the intercept can be found in part 2 of the statistics handout. I don't know how many of you will look up, but it's there. Okay. All right. The other concept we saw is linear transformations. So linear transformations, we have x, y. Let me show you an example that we did. Is this too easy, or is it okay that I'm spending the time to review this? Because if you feel it's unnecessary, I can do something good. All right, so here is a problem in which we did, you look at the data here, x and y. If you just plot x and y, they look like this. X and y versus x looks like not linear. So what we do is to take the logarithm of both sides and try to plot the logarithm of x and the logarithm of y, which if you plot actually turn out like this. So here is the data, logarithm of y against logarithm of x. This looks linear, so we fit a straight line to this m and b. The problem doesn't stop with m and b. You need to get the equation for the original fit. How will you do that? So you start with y equal to mx plus d for the transformed variables. Substitute logarithm of y, logarithm of x, which comes out to exponent of b multiplied by x power m. Okay, this inverse transformation also is part of the problem. Okay, so now if you have this equation, this fits the data that we originally wanted to summarize or perform a regression on, this one. So this data is described by y equal to x power e power b multiplied by x power m. So you can expect combinations like this. That is, if you take the original data, here logarithm of y and logarithm of x have a linear relation between each other. It could be the case that log y and x have a linear relationship, or y and logarithm of x have a linear relationship, or log have a linear relationship. Any combination could appear in the example. Okay, so this example here talks about logarithm of both quantities, and then we develop the fit equation and then try to have the fit constants m and b, and from that the original fit. Okay, is it clear, or any questions? Shall I write this on the whiteboard? Might be simpler, or easier to understand. So let's start here. This is your data. Okay. How do you know whether to fit a linear equation to the data directly or if a transformation will be needed? How do you know that? Or how will you know that? You see if the slope is constant at all points, which if it is, you are okay to use a linear. Otherwise, you have to use the transformation. So you have, let's say, define y equal to logarithm of y and x equal to logarithm of x. And then if fit, let us assume y versus x is linear, which means y equal to mx plus b. And can I say solve for m and b? Will you be able to do that? If I say that, is that something you are like, okay, I can handle that? This m and b are based on the transformed x and y. Okay, so don't use this directly. You'll have to open a column, ln x, ln y, and work with that set. Again, those values will also be provided to you. You don't have to do the calculation. Yeah.
I guess you said that they could have a linear relationship with a non-logged.
Yeah,
area.
semi-log. Yeah.
How would that work to find v?
I'll go through that.
Okay.
So first thing is in the quiz or exam, you will be given a lot of information, lot more than you need. If you don't know what to use, you will be lost. So I'll give you x, y, log y, sum of all the x's, sum of all the y's, sum of all the logs, everything. You have to pick and choose what you need. That is the test. Okay. All right. So suppose you get m and b. Are we all together up to here? So now, what is y? Substitute for y and x. What is y? Natural log of lowercase y, m, natural log of lowercase x plus b. This is like writing natural log of y equals natural log of x power m plus b, or ln of y over x power m equal to b, which is y equal to exponent of b times x power n. With me so far? Good. When you do the solution for m and b, you also know how to get the confidence interval for y, can you? If you can do m and b, I also taught you how to get the confidence interval for y. Right? That is, suppose you are plotting y equals ln of y and x equals ln of lowercase x. Here's your data, let's say. This is y equal to mx plus b, or y equal to e power b times x power m. Everyone with me so far? Good. If you can do this, you can also get me the confidence interval on the uppercase y. Can you? Yes, no? Can you get these confidence intervals? You're okay? You think you can do this? No, I mean, see, you are given this original data. After you write them as logarithm, you can even for some time forget about the original data. This is your new data set, which is linear. So if you give you a linear data set, it's like the first problem. Can you get the confidence interval? Right? So let's say we call that Ci, we give it a symbol, we'll call it Uy, or it's also called the uncertainty in Y. Okay. What I want to get is the confidence interval for our lowercase y. I want the need the confidence interval for y. Ciy, which I'll give a symbol uy, and that is uncertainty in y. We need this. Okay. How do we get this? So you have this y equal to ln of y. Okay. So if I rewrite this, y equal to exponent of y. Okay. If I want a small change in y, that will be partial derivative of y with respect to y multiplied by a change in y. Where is this coming from? This is your good old calculus. If y depends on another variable, the change in y is the slope multiplied by the change in the other variable. Okay. When it comes to measurement theory, we write it as uncertainty in y is partial y over partial y multiplied by uncertainty in uppercase y squared square root, so that any negative sign goes in. What is partial derivative of y with respect to uppercase y? E power y. Right? Derivative of e power y is simply e power y. So this is nothing but e power y times uncertainty in y. So this is the plot of y versus x, the transform variables. If you look at the original data, it's going to look something like this. Power law, y equal to e power b x power n. So if I want to draw the confidence intervals around this, it has to keep up with the increasing magnitude. It can't be a constant. That uy, this confidence interval is what we refer to here. This is the confidence interval on y. Okay. So the concept I'm introducing to you is this one here. How do you get the uncertainty in the quantity that you are really seeking in terms of the quantity which is just an intermediate? Okay.
So like the exponential type, this would be kind of a converted from like taking data points to a log. This is how you get to CI. The other version, you go through a lot longer process than, right? But you can't take these values and then say, oh, my X and my Y, and then do like Y fit X. You can't.
No, you can't do that. You have to go see that there is a certain sensitivity between this lowercase y and uppercase y. The when there is a small change in the uppercase y, if I tell you if log of something changes by 0.1, you would tell me the quantity itself changes by exponent of 0.1, right? That's what this is. If there's a small change in y, it has to be a change in the lowercase y, but it also has to go through the ratio in which y and, for lack of a better terminology, y and y vary with each. Okay. So this is again. I know this is a lot. I'm actually pushing you guys much more than I've done in prior versions of this class. But what I want you to take from this is at least the acknowledgement that the uncertainty in y is not just like drawing a band around this. It is actually paying attention to the scaling between lowercase y and uppercase. Okay. Whether all of this will actually appear on the test, don't worry about it. What is going to appear though is you will be given a data set. You will not be told anything else. You'll be told to fit a 2-parameter model to the data, and just told that apply any transformations as necessary. That's it. I won't tell you take logarithm, take this, do that, nothing. I won't tell you anything. Just one column of data and one sentence. That's it. You are supposed to get this sort of an equation. Now, this is when y versus x is linear. Suppose y versus x is linear. That is y equal to mx plus b, or y equal to m ln x plus b. This is y equal to ln of x power m plus b, or you can write this is so this is ln of e power b, right? So this is ln of e power b times x power m, or this would be, yeah. So y equal to ln of e power b times x power m. This is assuming instead of needing both ln x and ln y, you just use ln x and y, semi-log. You can also think of the other combination where suppose ln y, or sorry, suppose uppercase y versus x is linear. So you'll have y equal to mx plus b, or ln y equal to mx plus b, or y equal to e power b times e power mx. All these combinations of data could come up. So what do you do as a strategy? You are in the test, you are given a column of data and asked to fit a 2-parameter fit, nothing else. What else will you do? Or where do you start actually? Yeah, first step is very much that. Thank you. So first you look at your original data, do the slopes, and the slopes will not be constant because problem 1, I'm going to make it a linear fit with confidence interval. Problem 2 is going to be a non-linear fit with a transformation. I'm again telling this, you can take my word. Problem 2 is non-linear fit with a transformation, with a linear transformation. So you can start with, I'll also provide you this both log x and log y. So you can start checking if any of these combinations is actually turning out to be a linear fit. It could be this, it could be this, or it could be this. That you have to spend some time to correctly make a judgment call. Okay, problem 2 is this. I'm telling you right here. Once you identify which of these cases is actually applicable to your situation or your data set, then you have to work out m and b, and then finally get the equation for the fit that we want. Question? We have like 25 minutes. Shall we do two examples similar to the two problems in our quiz? Okay. We'll start with problem 2 because that's the more complicated one. Okay.
This part is this.
Yes. Yes, this is very much on the quiz, problem 2. I think I did most of the examples in the book. So let's try problem 17.10. If you have the book, problem 17.10. So this is an example typical of P2 on the quiz. Okay, problem 17.10 from the book. Oh, let's do problem, sorry, 17.910. Okay, so you are given x and y values. Okay, 0.4, 800, 0.8, 975, 1.2, 1500. So it will be given to you. Okay. First step is for you to understand whether a linear fit is going to be enough for this data set. How will you do that? Linear data set, slope, right? So compute the slope here. What do you get? This is 700 units divided by 0.3, which is 2333. And if I take here, the slope is 175 units divided by 0.4, which is 1750 divided by 4, which is 437.5 something. So anyway, clearly the slopes are different. Slope is changing. So which means not linear. That is, y versus x is not linear. So when I say two parameter fit, I can vaguely say even a linear equation is a two parameter fit, but this data as written is not linear to begin with. So then you would have, let's say, x equal to ln x and y equal to ln y. So the problem statement can be worded in a couple of ways. One is I might just give you this column, which is your clue to seeing that the data is not linear. If it were linear, I don't need to give you this. Or I can say fit and fit a model or fit an equation of the form y equal to ln x plus b for this data. I might just say, give you this equation. If I give you that, you don't need ln x, you just need ln y, and x is already there. Either I'll give you this data or I'll give you both x and y and confuse you further. Okay. So let's say we go with this. Let's say we tell you this y equal to ln x plus b. So you need to compute what is ln x, what is the fit constants. That my marker? Oh, wow. Okay, I got it. Okay. Problem 17.10. Okay. So problem 17.10. Can somebody read the data for me so I can save some time? X and Y, X and Y. Thank you. Yeah. Hmm. Hmm. Two and what? 29. Okay. Okay. So here is our X and Y. And when it appears on the exam, you're going to get this two additional column, ln X, Y equal to ln Y. So this is log of X. All right. So now you need to figure out which combination to use, or it should be told to you. Okay. If I tell you use this form, Y equal to ln X plus B, it's easier for you. Let's just check. Let's just check. Okay. If you don't make any assumptions, you would still check the slope. So that doesn't seem to be really the case. It's not that the slope is constant here either. So if you see here, the slope actually changes. So ln X and ln Y is not the correct combination. We'll try Y and ln X. Okay. So Y and ln X, ln X, ln Y, Y or ln X and Y. What will that be? This isn't either constant. So the slope between ln X and Y is also not constant. We'll try, what's the one remaining? X and ln Y. Try X and ln Y, okay? X and ln Y. So this will be X, ln Y is here. Okay, so among the three, which do you think is least terrible? Third, right? Third, X and ln Y. So we'll use X and ln Y. Okay, so just all. By the way, remember only this table is provided to you, and the corresponding sums, that is sigma X, sigma Y, everything will be given to you. Okay, so now you want to write X and ln Y. Okay, so X is here, ln Y is this. Just for clarity, I'm putting them separately. So you have decided that this is the data that you want to fit the straight line. And from here to getting M and B, you're okay, right? If I give you this, or if you narrow this down, you're going to get M and B. And on Excel, what I'll do, On Excel, what I'll do is insert a fit and I'll say display trend line. And that trend line will say linear, displays the equation. Wait. Come out right. Yep, there we go. Yeah, 1 second. Yes, what's the question?
So during the test,
Mm.
because we won't have access to like, well, you try to make the data as perfect as possible for the slope.
Yes, it won't be very noisy or anything. One thing I'll tell you, the challenge you're going to navigate is, I'll give you X, Y, uppercase X, Y, 4 columns. And for each of those, I'm going to give you sigma X, sigma Y, and those things. So it's going to be a lot of summations that you will see provided to you. It's like saying, if X, Y were a combination, or if X and Y were a combination, or Y and X were a combination, and X and Y are a combination. You will get all combinations. Now you have to select which one. That is the confusing part.
And in this case, right, the slope would be different depending on the point we took. So there would be a amount of error with answers if we took different points, right?
No, that won't be a problem. You have to make a judgment call looking at the spread of values. Look at this spread, 250 to 5,000. Look at this spread, about 0.5 to 1.
Yeah.
Look at this spread, about 0.28 to 1.55. That's why I asked you the question, which is the least terrible option, which is this spread. Okay. Okay, so you got M and B, okay? 0.82 and 6.30. How do you now interpret that M and B? What is this relation between? This Y is uppercase Y. I should write this as uppercase Y. Uppercase Y is 0.81 times X plus 6.30. How do you rewrite it? What is uppercase Y? Ln Y. So Ln Y is equal to this. So Y equal to exponent of the right side. That's it. That's your final equation, final fit equation. Okay, Y, lowercase y, I'll write it here. Lowercase y is equal to exponent of 0.8187x plus 6.3037. That's it. The problem stops here. The question would be, get a 2-parameter fit for the following data. This is the 2-parameter fit. You can stop here. Okay. Let me check something real quick here. I already made the exam. I just want to make sure I don't make this too complicated. Okay, actually, I'll just say this for now. For the exam, for the quiz, you are getting a log plot to keep things still manageable within that 40-minute time frame. You are getting this in the exam. You're going to get a column of X and Y and a column of uppercase X and uppercase Y, which is ln X and ln Y. what you are essentially going to do is to fit a straight line between ln y and ln x. This is what's coming on the test. Of course, the numbers will vary, and I'll see how you do the calculations. There is no like mystery otherwise. Okay, not this problem, but a problem like this. Okay. So this as you can see is a very actually I would say a very interesting topic. As I started preparing for this curve fitting, it's a lot of it that I did as a graduate student, trying to get data, summarize them, get uncertainties from the fitting. All that came back to me. So one particular thing you should be aware of this is the fact that you have, let's say, an equation y equal to or y equal to mx plus b, okay, which you can rewrite as ln y equal to m ln x plus b, or y equal to e power b times x power m. Okay. If you want the uncertainty in y, I just want to re-emphasize this because almost never you will handle the raw data by itself. You will always transform it into something like a linear or something simpler, and you will get an uncertainty in y. And eventually your boss or your advisor or whoever is your next in line is concerned about this quantity and not this quantity. So they'll want to know what is the uncertainty in y, which in this case would be partial derivative of y with respect to y multiplied by uncertainty in y. This is again going something that you will be using moving forward, not necessarily on the quiz. Okay, but I want to make sure you understood this. All right, so we did one example similar to P2 on the quiz. Shall we do one similar to P1? Right? Okay. So similar to P1 is going to be I would say some of the problems we already did, especially problem 17.3. We did. You will be given this table. Okay, I reiterate. You will be given this table and these values: sigma x, sigma y, sigma x squared, sigma xy. All these will be given. Now you have to compute these four quantities. Sorry, you have to compute m and b, and then these four quantities. This is the problem statement. Okay. You seem to be very worried.
It's just like a lot of things to calculate in a certain time.
Actually, in the format, you'll be having like 6 lines. I'll exactly tell you what to calculate and leave a blank. You just need to fill in the blanks. Okay. So the first question is m is equal to b is equal to the first and second. Third line is standard error of the fit is equal to standard deviation equal to t statistic equal to lastly confidence interval equal to. So it's 6 fill in the blanks that you need to fill up in sequence. You don't have to even think this on the fly. If you follow my sequence, you will finally get the answer. All I'm looking for is, can you put these formulas in a line and do the multiplication? I didn't post a mock quiz. This is any combination of these problems you can treat. I mean, I would ask you to actually do all these problems again by yourself and check with the Excel sheet.
Like I'm saying it, just like visualize what the layout looks like on the quiz.
I would show you if I had not already submitted a quiz for her. because I have to submit that quiz 2 days ahead of time each time. If I show you that, then I have to go back and get that exam back and prepare a new quiz for her, since she takes it separately. So you can,
But you're giving the summations.
I can do one thing.
Right.
I can take that exam, pick another problem with different numbers, post that as a mock tonight or by early tomorrow morning. Okay, I came here today thinking that going over all this will declutter it. I don't know if I helped or if I made it more cluttered. But one thing for sure is I'm including more content than I've ever done for this class in regarding to statistics. So if you feel this is all a little bit too much, I need to tell you what is not clear so that I can calibrate myself. It's okay. It's a lot, but you can still manage it. That's what I'm hoping. Okay. So today and tomorrow at least, excuse. So tomorrow afternoon between 1 to 5 or 1 to 4, I'll be in my office. So if anybody wants to come and talk, I'll be available. I'll try my best to post the mock tonight. Okay. Any other questions? No? Okay. So we'll see on Thursday. Please be on time. And your homework 3 is also due on Thursday. You still remember that? Yes.
So for the exam, not the quiz, but for the exam, will be something similar to this as well.
Yes, that is in terms of the question, we still want to keep the same layout. Give you like a sequence to fill out. If you miss the third step in the sequence, fourth and fifth and sixth are not going to be correct for you. So you have to get all of them right, or at least go. At least if you make a mistake only in the sixth step, you are losing less. Losing less. Okay. I'll post this file. Okay. Yeah. Yeah, I'll try to post the mock exam today. Okay.